Hi everyone, welcome back. Today what we're going to do is I'm going to show you how to do a one-point linear perspective drawing. So linear perspective is a drawing technique that comes to us out of the Renaissance. But it's not just a technique. Linear perspective is a drawing trick. And I always feel a little bit conflicted about drawing tricks. We may have talked about this in class at some point, but the reason I say it's a drawing trick is because linear perspective is not the way we actually see the world around us. Now, some people will take exception to that. They'll say, look at a linear perspective drawing, and they'll say, well, of course that's the way that I see the world. It looks so real. But the truth is, we don't see the way that linear perspective guides us through this particular technique. We see with all of our confidences and all of our insecurities, we see with our eyes, yes, but we see with our heart, we see with our mind, we see with the conditions that we're currently in. Our heads move, our vision changes. We pay attention to one thing and maybe not so much another, and then maybe that reverses and we start paying attention to something else. In other words, drawing isn't some fixed end that we're after, but drawing is a relationship that we're engaged in. And that relationship includes what it is to see and experience the world as a human being. The problem that I often have when I see drawing tricks is that they try to bypass the experience. Now, I'm trying to be fair here. I think that there's some value to some of what drawing tricks tell us. But they can be applied in such a way that we start ignoring the actual experience of drawing as an engagement of the world. Like, for example, a lot of times you'll see these magazines or pamphlets or books in art supply stores, and they'll say how to draw a duck, right? Or how to draw a portrait, or how to draw, and they all seem to kind of base their process on the same thing. I mean, you start with an oval, right? And then you mark off on that oval like where the center is. And then you mark off the three parts on that oval where you're going to place the eyes and the nose. And you come down halfway between the brow ridge and the bottom of the chin in order to mark off where the bottom of the nose is going to be. Now, these are important kind of concepts in terms of the physical proportions that we learn out in front of us. But you don't start a drawing this way. This isn't what you're seeing. You're not seeing an oval. You're not seeing a few lines. You're not seeing, this isn't how to draw. This is an important concept, but the problem with drawing tricks is they often start at a prescribed end. In other words, you can ignore how to experience a portrait. You can ignore how to experience that person. You can ignore the fact that they have a name. You can ignore the fact that they have blood, that they have tissue, that they have bone, that they are just like us. They are in our space and sharing our space. You can ignore what it is to engage them as a human being with your confidences, with your insecurities, with all of what it is to be in a human relationship, and instead start trying to prescribe that this situation must fit the formula. That's the problem that I have with drawing tricks. And I want you to understand that as I go through this today, that I don't want you thinking that linear perspective is the way to draw what we see. But instead, linear perspective gives us a certain understanding from the trick that allows us to bring a different level of understanding to when we're drawing from observation. So we're never going to separate drawing from observation and replace it with some prescribed end of the trick, okay? So now, with that said, let me explain to you a little bit why linear perspective is not the way we actually physically see the world. So there are a couple of precepts to linear perspective. Linear perspective is based on a couple of truths, okay? So those truths are these: that things as they move far away from us in the distance will get smaller, and things that move closer to us, they get visually larger, right? So that makes sense. The other precept is a little bit more complex, and that is that parallel lines, as they recede away from us in space, will seem to converge on the horizon line. Now, I'll explain that, and you'll see it here in just a moment. But let me stop there for a second and point out those precepts. Realize that linear perspective is a Renaissance invention. Well, how could that be, right? Because does that mean that prior to the Renaissance, nobody knew that things far away from us looked smaller? Well, no, of course they did. Everybody always knew that. Or does that mean that somebody in the Middle Ages who's standing on a road and they see the road diminish into the distance to a fine point would look down that road and say, oh, I can't go down there, it gets too small? Well, no, of course, people have always known that parallel lines, as they move away in space, seem to get closer together. And people have always known that things in the distance look smaller than things that are up close. We've always known those two precepts, and those two precepts are true. So why do we say that the Renaissance invented linear perspective? Because the Renaissance was looking for a means to depict the world more convincingly. Now, you notice I don't say necessarily more realistically. Part of the Renaissance ideal was to idealize. So they're not talking necessarily about being more realistic, but they are definitely talking about being convincing. And a lie can sometimes be convincing. So what the Renaissance does is it takes these two precepts and it formulates an entire formula around them, that if you apply it consistently in the formula, you will create a convincing result. Now, with everything that I said about drawing not being a trick or not being a lie, why is it that we would do this at all? Well, I'll get to that in a minute, because it does give us the ability to do certain things that without it, we otherwise wouldn't be able to do. So let's take a look at the basic precepts as they happen on a page. So the precept is things up close are larger than things that are far away, and that parallel lines, as they recede away from us, will seem to converge on the horizon line. So what is a horizon line? The horizon line is our eye level. So the horizon line equals our eye level. Now, that is whether or not we're talking about us as the artist or us as the viewer. It will read as the viewer's eye level. So now, if I were able to knock out all the walls and knock down all the trees and look all the way out to the horizon, the way that I might be able to do if I was on a beach and looking out at the flat water all the way to the horizon, I would notice that the horizon line actually does appear to be at my eye level. And if I lower my body down, that horizon line tends to move with me. Okay? If I go up in the air, that horizon line seems to raise up and I see more of the ground plane. So the horizon line refers to the artist's eye level. Now, if I'm making up a drawing, I can decide to put that horizon line anywhere that I want. If I put it very low, it's going to make an image look like I'm looking at everything from a very low vantage point. If I put the horizon line high, it's going to look like I'm looking at everything from a very high vantage point. So let's take a look at that. If this is my horizon line, and I have, say, an object out in front of me, okay, I can put that horizon line here, and I can put, say, let's just take a square, and we'll turn it into something at least similar to a cube, okay? So this is the front plane of my, what will be my cube. Now, notice that I've put the horizon line dead center, which means my eye level is looking right at the center of that cube. I'll erase out a little bit so that it doesn't get too confusing. Here is, right now, just my square in space with my eye level at the center. Now, as things move away in the distance, they become smaller. And we know that a cube is actually 6 squares put together, right? And because the cube has 6 squares that are all the same size, the square that forms the back edge of this cube is further away from me. Although it is physically the same size as the front of the cube, it will appear to be smaller. So let's say there is a back edge to this particular square. It must look smaller. Now, I'll explain to you what I'm doing here in just a moment. Okay? That back edge of the square might be right here. Now, you can see through this square a little bit. And you notice that if that were the back edge of the cube, okay, we can make it kind of transparent for the moment. Okay? Here is like an open box in this space. And you notice the back edge of this cube, which is indicated in here, is smaller than the front square that indicates the opening of that box, right? Pretty nifty. But the other premise is also demonstrated here. You notice that these two lines on the side of the box are actually getting closer together as they move away in space. That's what we mean when we say parallel lines, lines that run with each other, right? Never actually connect, but run parallel to each other. Those lines will appear to get closer together as they move away in space. And not only that, but the precepts here are applied to the rules of linear perspective as developed in the Renaissance, and that says that those lines will move at a very specific angle. They will move at an angle which causes them to meet at the horizon line, the viewer's eye level. So we get a fairly convincing shape in space. I'll remove everything that's not necessary here, all the little guidelines. Okay? We get an image that seems to be sitting naturally in this space if we follow those rules. And this point, where those parallel lines as they recede away from space, where those lines meet, we call the vanishing point. The vanishing point. And what the rule tells us is that everything else that is parallel to this particular cube or box is going to follow the same set of rules. So, in one-point linear perspective, all lines that are flat to my plane of vision. Now, understand what I mean by that. When I'm looking out in front of me, I have a plane of vision, okay, right here. Okay, it's a flat plane. It's flat to the positioning of my eyes. Anything that is flat, moving horizontally on my plane of vision, is going to remain strictly horizontal and vertical. So you notice here, strictly horizontal lines forming the top of this cube, and strictly vertical lines forming the left and right edges. And just like this front square is flat to my plane of vision, the back of this box is also flat to my plane of vision. So the same rule applies. Strictly horizontal lines for the top and bottom, strictly vertical lines for the sides. You see that? Okay, so that's one part of it. Now, lines that are moving away from me in space, in other words, they're not flat to my plane of vision, but they're following my line of sight away from me. lines that are parallel, meaning they never actually come together, lines that are parallel moving away from me in space on my line of sight, not my plane of vision, but my line of sight, those lines will seem to get closer together and converge at the vanishing point. So the sides of the box move at the angle that would bring them to this point on the horizon line that equals my eye level. Pretty simple, okay? Now that's the rule of one-point linear perspective. Lines that are flat to my plane of vision, strictly horizontal and vertical. Lines that move away from me in my line of sight, as it moves away from me, parallel line will seem to get closer together and converge at a vanishing point on a horizon line. That's the basics of one-point linear perspective. Now, you look at it and you say, well, that's pretty convincing. I mean, you can throw anything else in here. Like I said, as long as it's parallel to this box, I can decide I can put a shape down here. Okay? Here's another square. Now, if there was a cube happening here, okay, these lines would go back to the vanishing point. Let's make it an open box again, and we'd say, okay, here's the back edge of that box. The back of that cube is smaller than the front of the cube because things as they move away are smaller than things that are up close. Here's the back of it. We're going to see just a sliver, hardly anything of the side of this box here. Okay? And every line that's moving away from me in space, and you can see what happens. And I'll just take out the excess lines that make it look quite so transparent. And here's another box in space. I would see just a tiny little bit of this angle right in here. Okay? There's another box in space that sits in the same space as this one. If one were floating up in the sky, right in here, I would follow the same set of rules. This would go down to my vanishing point. Smaller square behind. I'm putting them all very, very close to that vanishing point from left to right. And here is a smaller box floating up in the sky according to the same rule of linear perspective. I can continue to go on and on, guys. I can add more shapes in here. I can add more boxes. I can keep going through this. And everything is going to become more and more convincing the more it is supported with additional forms that follow the same set of rules in the same drawing. And you can look at it and you can say, okay, well, I get it. That's kind of convincing. Why does Matthew say that's not the way that I see the world? Because that obviously is the way that I see the world. Why don't we show this particular drawing trick earlier in a drawing course so that we can just bypass all of that nonsense about looking at the stuff in front of us and just apply the rule because look, it works. Well, here's the thing, is it doesn't actually work. I mean, it works to be convincing, and that's the goal of the Renaissance. But it doesn't work to necessarily tell the truth of your experience for all those reasons I mentioned earlier, but also just physically. Think about the definition of a cube. A cube is a square in 3 dimensions, and it is made up of 6 squares of equal size. Now, consider the fact that here, based on the rule, we have 2 vertical lines and 2 horizontal lines. 2 vertical lines here and here, 2 horizontal lines to form the front of this cube. Makes sense. But now let me ask you, where would you have to be standing in order to see a perfect square when you're looking at a cube. If I move to the left of it, then the side that's farther away from me is going to be smaller. But you notice the side here to the left of us is no smaller than the side to the right. If I move to the right of it, the side over here is going to be smaller than the side over here. So I can't have two equal measures to these vertical lines unless I stand in only one position, and that is dead center to that cube. I would have to be standing right in front of it. The only way I could see a square is if I was standing right here, looking straight at it. And where would the back of that cube be if I was standing right in front of it? If I was standing right in front of it, the back of that cube would be inside here somewhere. In other words, I wouldn't be able to see it at all, because by the very precepts of linear perspective, the back of that cube has to appear smaller. If I'm standing right in front of it, dead center, the back of the cube is hidden from the front of the cube, by the front of the cube. So the thing is, guys, what we get in one-point linear perspective is we get a distortion of space. That when we look at it, we say, oh no, that's the way that I see. But it's not the way that you see at all, because this isn't a cube. It can't be. You would not be able to see the side of this cube at all if you were seeing a perfect square for the front of that cube. So linear perspective, in terms of at least one-point linear perspective, is definitely a lie that convinces us. But it does allow us to do certain things that without understanding this trick, we wouldn't be able to do even from direct observation. And that's the reason why it's such an important thing to understand. So what is it that linear perspective allows us to do that we otherwise wouldn't be able to do? In other words, why is this trick, which isn't really the way that we see, something that's useful to drawing from direct observation? So here's the thing. Think about the fact that when we're drawing from a still life or even a landscape that is so far away from us, in both of those cases, the entirety of what we're drawing is within our field of vision. In other words, I look at the still life and the entire still life exists within the area that I can focus on. If I'm looking in the distance, the entire landscape that I'm looking at falls so far back that it falls within a field of vision that I can see all at once. But what happens when we look at an interior space, for example? An interior space which is close enough to us so that we can't picture the whole thing without the movement of our head, kind of scanning in a panoramic view. How do we deal with drawing something that doesn't fit within our field of vision? Well, linear perspective can help us do that. So what I'm going to do is I'm going to show you how to apply this when you are dealing with an interior space that requires you to look over here at one moment and then look all the way over here at another moment. I certainly can't, as we do in class, measure the entire thing with a consistent horizontal if that horizontal necessarily has to change as I move across the span of area that I'm trying to look at. So what I'm going to do is I'm going to draw the entire room out in front of me. I'm going to choose an area way over here to my left as my starting point, and I'm going to choose an area way over on this other side as my ending point. What I have to do first is I have to determine, by looking out in front of me, which of the walls in front of me are what we referred to earlier as flat to my plane of vision. In other words, when I look back into this space, which walls are flat to my plane of vision and which walls are receding away from me in my line of sight. So, where you want to start is you want to start with the furthest wall away from you. Now, I know that you can't see the room around me, and it doesn't really matter, because all I'm going to do is I'm going to look for information out here, and then I'm going to start transcribing it into this system. So I'm going to start with the furthest wall away from me. And I'm going to take a string. Yes, I am still going to be measuring here. And I'm going to check with the string the height versus the width of that wall. I need to know what shape I'm putting down to begin with. Now, I know that that shape is going to consist of only horizontal and vertical lines. Remember the rule. Anything that's flat to my plane of vision is strictly horizontal and vertical lines. So I look at the wall furthest away from me and I measure with my string how the height of the wall compares to the width of the wall. Now, when I take that measurement, what I'm seeing is I'm seeing that the height of the wall is a little bit less than a third greater than the width of the wall. So it's a little bit less than a third more than the width of the wall. So what I'm going to do is I'm going to start with that particular rectangle on my page to represent the furthest wall away from me. So let me draw that out here. Let me grab my charcoal. And right here in the center of my page, now it has to be relatively small. Usually if people go wrong here, what they do is they make it too large, which doesn't allow them to draw a lot on one side versus the other. So notice the scale that I make it. If I make the top of this wall only about this wide, maybe a little bit less, maybe here to here. If that wall is represented by a length that wide, remember the height of the wall is a little bit greater by just less than a third. So I'm going to measure this out, and I'm going to take a look at the width of the wall. A little bit less than a third more would be somewhere about here. I'm going to turn the string and I'm going to take a look at where that wall would come down to, and I'm going to put two vertical lines. Now remember, just like every other time we practice, this doesn't have to be absolutely perfect to start out with. I can straighten lines out as I go. So there is a dog barking near me. So what I'm going to do is I'm going to finish this one rectangle as my starting point. You can use a straight edge. Now I'm using a heavier piece of charcoal here, and sometimes when you're doing this, the tendency is you want to use something thinner than this, like a charcoal pencil. But I prefer to stick with the heavier charcoal because I know that ultimately what I'm going to want to do is make this into a value drawing. And I want to impart the pigment to the page. Okay, so this is where I'm going to start. This represents a wall that I'm seeing out in front of me far away, and it also has been measured to equal the proportion of that wall. So now every other wall in my environment that is flat to my plane of vision, the same way as this wall is, okay, every wall is going to follow the same rule, strictly horizontal and strictly vertical. But walls that are moving away from me in my line of sight, they are going to recede back to a vanishing point on a horizon line. So the next thing I need to do here is I need to determine where my horizon line is going to be. And in this case, because my height in relationship to the walls around me puts my eye a little bit higher than midway, I'm going to do the same thing here. If this were the wall and I were standing right next to it, my eye would be a little bit higher than center. So I'm going to put it right about right there. You notice how I'm just marking off where the height of my eye would be. Now remember, the system allows me to be inventive here. If I want to draw this entire space, I'm just putting a line through to indicate my horizon line. If I want to draw this entire space as if I were down on the ground looking up, I don't have to physically get down on the ground in order to do that. All I need to do is lower the eye level, the horizon line, within my drawing, and when I plug everything in, it will look like I drew it from down below. If I wanted to make it look like I was drawing the room from up above, up towards the ceiling, I would simply raise my horizon line. So I can invent this space in a way that it doesn't require me to get up on a ladder or lay down on the floor. That's part of the inventiveness of linear perspective. So now this represents my horizon line. You start off with the back wall, right? And then you put your horizon line in. Now, where is my vanishing point going to be? My vanishing point is going to be wherever I decide it to be. If I put it dead center, it will draw this room as if I'm standing in the center. If I put my vanishing point over here to the left, if I put my vanishing point over there to the right, it will likewise move me as the artist or the viewer visually left or right. I'm going to decide to put my vanishing point a little bit to the left of the center of this wall because that seems to be about where I'm standing. So I hope you can see that. Now what I'm going to do is I'm going to start drawing the walls that extend from this back wall towards me. In other words, these are the walls that instead of moving in my plane of vision, flat to my plane of vision, these are the walls that are receding away from me in my line of sight back to a horizon line. So notice I know where this line is going to start because the wall meets the ceiling of this back wall right at the corner. And I'm going to use a ruler or a straight edge. You can use a cut piece of cardboard or whatever you have at hand. I'm going to use the ruler in order to put it to my vanishing point right through the corner of this first rectangle. And I'm going to draw this line out. Now, I don't have to know where to end that line right now. That's not essential, okay? I'll figure that out in just a moment. But I'm going to continue. I'm going to look down towards the bottom of the wall. And by the way, there's a lot of stuff in there, right? There's stuff in the way. I don't really see that corner very well. I don't have to because I know that corner starts right here. So I'm going to draw the next line that extends out from the bottom of that wall, and I'm going to bring it back to my vanishing point. And the angle of that bottom part of the wall is going to be right here. Okay? Notice these two lines, which represent the top and the bottom of the wall that recedes away from me in space, go back, meet the corners of the previous wall, and they extend to the vanishing point. Now I'm going to do the same thing on the other side. This extends back to the vanishing point and forward in this direction. Now what I need to do is I need to determine how much of these walls am I going to see. Now you can almost tell here, it's kind of like a hallway that I'm looking at right now. It will build from here. So again, I don't want to separate this so much from what I see that I'm just making it up. I want to actually take a measurement here. How much of this wall do I see? And I'm going to compare how much of that wall I see to what I already have in my drawing. How much wall do I see here compared to the width of this back wall? So I'm going to measure it. And when I take that measurement, I know I'm standing probably right in front of the camera right now. I find that the width of this wall extends the distance of about that far across the back wall. See what I'm doing? I'm comparing the width that I see here to how far that width would extend across this back wall. It extends about 3/4 of the way. I'm going to make a little mark right here to indicate where the edge of that wall is. And remember, this will begin the edge of another wall that is flat to my plane of vision. So this line will stay absolutely vertical. Use the edge of your page to judge whether or not you've got a vertical movement there. And here is the outside edge of this wall. Now what I'm going to do is I'm going to show you the next wall, which is flat to my plane of vision. Which means that the next wall that happens over here is in the same plane as this back wall. It's flat to my plane of vision. Again, remember the rule. The rule is that anything that's flat to my plane of vision, strictly horizontal and vertical. So I'm going to take a look at that wall, and I'm only going to make vertical lines for the two sides and strictly horizontal lines for the front. There and there. Now, how wide should this wall be? Again, I'm going to measure it from my environment. When I check it, the width of the wall that I can see is actually a little bit greater than this back wall. So I take that measurement, add just a little bit to it, come back here. Yes, it's a very, very small wall. And it's made, because it's flat to my plane of vision, with strictly horizontal and strictly vertical lines. Okay, so now I'm going to move to the other side over here. I know this is a long drawing and I could be standing in your way quite frequently, but I'm going to start putting in the lines for this side, sticking to this. There's a funky little wall that happens over here. I'll show you how we're going to handle that, but let me get a few more of these in following the same rule. Okay, so take a look at what has happened, all right? I just took a little bit of a break from the filming part and continued with a couple of the other walls, following the same rules as you saw me apply at the center and the two side walls here. So you notice those walls that are flat to my plane of vision is this back wall, strictly horizontal lines at the bottom and the top, strictly vertical lines on both sides. This wall right here is exactly the same position as this back wall. It is flat to my plane of vision. Now remember, when I look in the space out in front of me, I'm actually seeing, because of the reality of where I'm standing in the space, I'm actually seeing this as an angle out in front of me. I'm not drawing here from direct observation. I'm taking information from direct observation, but I'm applying it, plugging it into a drawing trick from the Renaissance. So don't try to draw the angles as you see them. Simply stick to the rules of the system. So even though in my actual space I see this at an angle, I'm nevertheless drawing this wall, because it is the same as that back wall, with strictly horizontal lines and strictly vertical lines. So I've got a rectangle here, and I've got a rectangle here, and I've got a rectangle here, with strictly horizontal lines and vertical lines, planes that are flat to my plane of vision. Those walls that are moving with my line of sight from the foreground into the background are moving away from me, and thus those walls are defined top and bottom with lines that extend to the vanishing point. You notice if you take any of these other walls, this wall here extends to the vanishing point. The top of that wall, it extends to the vanishing point. This wall here extends to the vanishing point. This bottom part of that wall there extends to the vanishing point. These lines on the outside of this far wall extend to the vanishing point. That's how those walls are created. Now, remember I said there is in my environment a funky little wall that happens over here. It is neither flat to my plane of vision, or is it extending back in space parallel to these other walls. Instead, it's cut into the architecture at an odd angle. Now, I'm going to deal with it, but I have to have what we would call an alternate vanishing point for that particular wall. What I'm going to do is I'm going to measure how far out that little part of the wall comes from the edge of this wall, and that's going to determine where that wall is going to end. So when I take a measurement out here, I find that it extends about that far out. So I'm going to put a vertical line down because that's one observation I can take from direct observation. I'm going to put that down while I know it. Here is the outside edge of that strange little wall. It's somewhere right about in here. That's the width of that little strange part of architecture that doesn't follow the rules of the rest of the drawing. Now, I say it has an alternate vanishing point, but because it's in the same drawing as the rest of these walls, it is going to stick to the same horizon line. In other words, I'm not going taller or shorter here. I'm seeing it at the same height as I'm seeing the other walls. So I stick to my same horizon line, and I'm going to extend that horizon line so I can see where it would be over here. Okay. And that tells me that my alternate vanishing point is happening somewhere along this line. Now, where along that line? Well, I'm going to have to take a little bit of an angle inspection. Now, we've done this in class when we're looking for the angles of boxes out in front of us. But in this case, I'm going to take the angle of the top edge of this wall. And the angle should be something along the lines of that. Okay? So I'm going to draw that angle in right here. Now, the bottom edge of this wall is not going to be measured that way. In other words, if I take that measurement from my environment, I'm going to find that it's not going to do what I want it to do because I'm fitting my information from my environment into this fabricated system. It's not going to be exactly the way that I see it. It has to fit into this system. And the way I can tell the angle of that bottom wall is fairly easy. I know that this angle here, it's eyeballed, but it is going to extend to an alternate vanishing point right there. And that alternate vanishing point tells me what the angle of the bottom of this wall is going to be. It has to also extend down back to that vanishing point. Now, this is the only really awkward wall that I have. Well, I wouldn't say it's the only awkward wall I have in my house, but it's the only awkward wall that I have within my field of view right here. So that is that odd little angle that happens at the edge of that small wall. Now let me get rid of this information so that it doesn't confuse us. We want to remember all of our other marks are not adhering to this alternate vanishing point. That was simply for this one odd-shaped wall. And now I will continue. And what I'm going to do is I'm going to continue to put in this side based upon the walls that I'm seeing here and whether or not they are flat to my plane of vision or whether or not they're moving away from me along my line of sight to the vanishing point. And I'm also going to drop in a few more details in here that will reinforce the perspective that I have elsewhere within the drawing. Okay, so I'll go ahead and do that, guys, and I will be right back to you. So I've taken this as the foundation of our drawing and I've added some things to it. I have straightened some things out. I have continued to apply this system of perspective to it a number of times in different locations. And the more and more I add to it, the more and more it reinforces the given perspective. Let me zoom out here so we once again have the entire page in view. Remember our original wall that we started the drawing with, and notice that the wall is made strictly with horizontal and vertical lines. Notice the additional flat planes that follow this same model. Notice too our original vanishing point and how the receding walls, those walls that move parallel to our line of sight as it moves into the distance, go at the angle that recedes to the vanishing point on the horizon line. Every other wall and every other architectural element that is parallel to these walls likewise recedes to the vanishing point. For walls or architectural elements and sometimes even furniture, you need to find an alternate vanishing point if they are not parallel with the regular walls in the room. For example, here is an alternative vanishing point for an oddly angled wall. But remember, even though it is an alternative vanishing point, it must still meet on the same horizon line as the drawing's main vanishing point. In addition to the oddly shaped wall, there's also an odd angle on the corner cabinet in this drawing, which also requires an alternative vanishing point. But again, notice how that alternative vanishing point meets on the same horizon line. Although linear perspective can be used to invent a space out of your head, remember that that's not what we're doing here. What we're doing in this drawing is we're combining observational measurements from our surroundings and we're plugging those measurements into a system of linear perspective. Because of that, you should expect a lot of change as your drawing continues to develop its measurement and refine its measurements. Take a look, for example, at an area right in here. When you look closely, you can see there have been a lot of changes, a lot of reevaluations as to how these measurements apply. And again, take a look at an area right down here. And notice the evidence of change and reevaluation that you should expect in your own drawing. And again, right in here. Remember, guys, to continue to measure, to continue to change, and continue to refine. Now, there are a couple of other areas in this drawing that I want to call particular attention to. Notice that the receding lines on the floor, as they are parallel with the receding walls, also recede back to the vanishing point. And that their horizontal lines remain horizontal. But also notice that as these horizontal lines and receding verticals create the shapes of the tile floor, that each tile successively gets smaller as it recedes into the distance. That diminution of size is not just random, but there's a way to figure out exactly how far back each square should go in relationship to the other in order to know where to place each successive horizontal line. In order to show you how to get the correct diminution of size as you recede into the distance, I'm going to simplify this for a moment and turn this into a slightly larger tile design, represented by the darker squares that you see here. So ignore everything else that you see here except for the red line. Now, that red line represents how wide the first tile in your design is. Now, the decision about how wide this line is going to be is really based upon observation. You have to decide, and you can do that by looking at the size of that tile comparative to other elements within your drawing. Now, once you've determined the width of your first tile, take those two corners and extend the lines lengthwise back to the vanishing point. Then draw another horizontal line to determine the back edge of your tile. Now, again, this is a visual estimate, but none of your subsequent tiles will be visual estimates. They'll all be based on the geometry of this first tile. What you want to do now is draw an X through the first tile. Drawing that X from corner to corner within that square gives you the perspectival center of that tile. Next, draw a line through the center of that X that recedes back to the vanishing point. You now have two rectangles inside your original square, as represented here, outlined in red. Draw a diagonal line from one corner of your rectangle to the opposing corner, and extend that line until it meets the receding line from your original square. Where these two lines meet indicates the back edge of your next tile. Continue the process and you have the correct diminution of size for each tile as it recedes into the distance. Despite the fact that you'll notice a distortion in the shape of the tiles as they move further and further to the outside edges of an image, remember it's important not to just try to eyeball this change in scale. The change in scale is dictated by the perspective, and the perspective is naturally going to distort things from the way that you're seeing them in your environment. But it distorts it consistently with the same vanishing point. It's the repetition of this system over and over that will convince a viewer that even these distortions in space seem to look right. Or perhaps better said, look convincing within the perspective of the given drawing. Now this is a little bit more complex. You can see what I've done here is I've drawn a grid in perspective just as I did the tiles. And you notice I've found the center of the entire grid to form the basis of what will be a circle in perspective in order to create this coffee table. You can probably tell that the coffee table appears to be a little bit stretched. In other words, it doesn't look quite as natural. And you could get a more natural shape to this table if you were to apply the gestural and mechanical measurements that we've practiced in class from direct observation. But again, it's important to remember that what we're doing here is a combination of observation and a fabricated system of linear perspective. The distortion that you're seeing here will be consistent with the development of the rest of the drawing, and you shouldn't allow the subtle distortions to make you think that you're applying the system incorrectly. Now, this drawing is not done. There are drawers in the kitchen, for example, that haven't been added to the cabinets. There's details to the microwave or the front of the stove. There is molding on the doors. There is a ceiling fan in the room. There's a couple of other chairs that can be added. Remember that when you're working on your perspective drawing, the more information that is plugged into the system, the more convincing, simply through repetition, the space becomes. Once all of the shapes of your subjects have been included within your drawing, you can then use the residual charcoal and charcoal pencil on your page to push that pigment out into your page so that you follow the surface contours of the surfaces and objects that you have, and then continue to develop the drawing according to the value processes that we have discussed and practiced in class. And one final word. You've heard me say several times in the course of this presentation that linear perspective is a fabrication. This is especially true of one-point linear perspective. And die-hard fans of the Renaissance spatial tradition might argue that a more natural-looking viewpoint is created through two and even three-point perspective. And in this, they'd be correct. But even two and three-point perspective are distortions of the way we see, for reasons I mentioned earlier as well as others. In any event, you pick your battles, and we don't have time to delve more into that argument here. For us, practicing one-point perspective gives an introduction to an important historical development in Western art history and an opportunity to further practice comparative mechanical measurements and, as always, the control and refinement of our medium. So, keep studying, guys, keep drawing, and stay safe.